So I will just get started right away. I will actually begin right away with the content of today's lecture, but then towards the end, I just want to go over how you are doing in your lab and direction of arrival estimation study and the algorithm development that you're doing. So maybe we'll spend a few minutes at the very end to talk about that. Okay, so we are right now looking at this beamforming, as well as today I think we'll get into this code division multiple access, which is considered as one of the technologies for non-orthogonal multiple access in 5G. So we'll get into that a little bit. We'll look at MIMO reception. We'll also briefly consider the deconvolution operation. And then maybe, if time permits, which is probably not going to be today, but maybe I want to give you kind of a theoretical underpinning of the several techniques that we'll be studying in the course of this lecture session. Okay, so this is the beamforming model that we have, I think we are all familiar with now. Okay, so we have seen this model multiple times before. Here the columns of this W matrix are complex exponentials of length n, and these complex exponentials are oscillating at different frequencies. And these frequencies are determined, in case of an antenna array, they are determined by the direction of arrival of a particular user. Okay. And we saw that we can look at that particular equation number 2, in multiple different ways. We can actually club it with the model that we have studied in CT509, and we can consider this as either the beamforming problem or more generally as the generalized demodulation problem. We have formulated the correlation matrix of X, but also we defined correlation matrix of W Hermitian. And I think we have made use of this matrix R several times. We looked at this vector Y, which is formed by taking the product of W Hermitian with our received signal vector X. And we saw that this vector Y, in many cases, has a reduced dimensionality, meaning it has less number of samples compared to vector X. Remember, vector X is an n cross 1 vector, whereas Y is just k cross 1 vector. And we have taken so far that k is less than n. In some cases, k can be significantly less than n. And so we are actually now here dealing with a smaller number of samples compared to the original samples. And we kind of glossed over it a little bit, but in general, we said that it is sufficient to just keep y instead of x. It is like the Nyquist theorem, where we have the continuous time signal, and we keep only some few samples of that signal. We throw away the entire continuous time signal except some few samples. And the Nyquist theorem promises us that as long as the number of samples is taken such that every second we are taking at least twice the bandwidth of the signal. So if we have 2 times b samples every second, where B is the bandwidth of the signal, then we are guaranteed to retain the same information that was there in that original continuous time signal. That is the promise of the Nyquist theorem. Something similar is going on here. We can have a much larger X. Maybe X can be a vector with 100 elements. And it may turn out that we can just remove maybe 97 of those 100 elements and keep only 3 elements of this vector Y. And those 3 elements are sufficient for us to then do the same type of receiver algorithm that we would have done on this original X. So a lot of the times this vector Y is used for signal processing expressions instead of relying on vector X all the time. Basically, Y is a compact definition of our received signal. It is succinct. It is kind of condensed, and that compression in the dimensionality is obtained without losing any performance aspects. Okay. So once we form that expression of Y, we said that our estimated symbols can be obtained by multiplying Y with inverse of the correlation matrix of W Hermitian. And as a result, we got this estimate as S plus R inverse of V, where V is the noise signal. Okay, we also looked at another way of estimating S, where instead of multiplying Y with R inverse, we add a small diagonal term to each diagonal element of R. Well, okay, not necessarily small, but we add some diagonal entity, some diagonal value to the diagonal element of R. And the value that we add is determined by the signal to noise ratio of different users. And we have seen that the resultant expression, which is called the minimum mean squared error expression, actually sometimes it performs better than the decorrelating detector that we have seen on the previous slide. In a specific, if this matrix R is, for example, non-invertible for some reason, then we can't even use decorrelating detector, but we can still use the MMSE. Okay, so that was the general solution of the beamforming problem. Now, we also saw that the same beamforming problem can be defined in an alternate manner, where what we are interested in is defining the vector W of beamforming coefficients instead of estimating the symbols directly. It is almost to be thought of as kind of a priori computation of the beamforming weight vector, and then using that weight vector to do real-time beamforming. And there we actually looked at a problem where we are given a set of requirements in terms of where our signal has to be, which are the directions from which our desired signal is coming from, and which are the directions from which the interference is coming from. And our requirement is to remove the interference and let the signals come in from the direction that it is coming in from. And this problem is highly relevant in today's technological development. This is very much the central aspect of the MIMO systems in 5G, especially the massive MIMO. And also for some reasons which are maybe aligned or maybe not directly aligned with the 5G or the next generation developments, our own Indian government's research organization, ISRO, is also very much interested in solving this type of problems. So they have given us one research project on which two of you are working, where we have to do something like this. And then they have also in parallel given us, in fact, two other research problems, one on which Komal is working, and another one in which Arushi is working, where some similar requirement is present. Although the details are different, but we have to essentially come up with the beamforming specification. I mean, we are given beamforming specification and we have to define an optimal beamforming weight vector. We went over the methodology for solving this problem, and we said that in fact the linear algebraic equation that we should consider to solve this problem is very much similar to what we saw on equation number 2 on that very first slide. The notations are different, but the algebra is the same. And in fact, we saw that the original x vector has now become vector d, where d is the set of specifications that are given to us. The matrix W, we are calling it now matrix H. The vector S of symbols is now becoming vector W, that we want to determine the vector W of beamforming coefficients. And in this particular formulation, the noise is not even there. And so we saw that we can actually perform the same type of decorrelation or MMSE algorithm. And now, instead of coming up with the symbol estimates at the output of the beamformer, we are actually now defining the coefficients of the beamformer that will give us the desired suppression of interference in specific directions, and otherwise it will give us good beamforming gain from that in the direction that the signal of interest is coming from. Okay, let us see. So we have considered these two different problem statements, and we have defined the decorrelating algorithm and the MMSE algorithm. Now, what I want to do next is I want to look at two other algorithms which are also very prominent. They are quite popular. They show up in a lot of literature. They come up in many papers in signal processing domain, in communications domain, and also this algorithms are not. I mean, they ultimately bear resemblance to the machine learning techniques. So they would come up also in the machine learning literature. In fact, the inventor of the algorithm is a very well-renowned research personality. His name is Norbert Wiener. And Wiener has made contribution in many different domains. But one such domain is actually the topic that we are looking at. And so there is an algorithm that that derives the name from his last name. It is called Wiener's algorithm, or sometimes it is also known as Wiener-Hopf algorithm. So that is one algorithm that I wanted to kind of bring in at this point. Another algorithm that I wanted to also bring in is the MVDR algorithm that we have already studied. It was developed by a mathematician called Kappan. And so this Kappan's algorithm, also known as the MVDR algorithm, is something that we can kind of bring in at this point. What has happened is I didn't focus on that over last several days. And so I didn't prepare the slides to kind of introduce the Wiener's algorithm or the Capons algorithm in the context of this decorrelation or MMSE detection. So we will have to park that topic as of now. We are on slide number 12. So let us see. One possibility is that next time we meet, I will have a new slide number 13, in which I will bring in this Wiener's algorithm and the MBDR approach and try to connect it with this decorrelation or MMSE. The other possibility is that I already have reserved a unification section at the end of this presentation. So maybe other possibility is that when we get to that unification step is where I will bring in this Wiener's algorithm and the MBDR algorithm. So let me think about it. But for today, let us move on to a new domain of discussion, which is the CDMA technique, known as code division multiple access. And so there, we are not talking about beamforming anymore. This is a completely different problem statement. It relates to when there are multiple users that are simultaneously connected to, for example, a base station or a particular satellite, or even it could be a set of sensors that are put in, let's say, some agricultural land, and those sensors are talking to the central unit, so-called central unit of this wireless sensor network. Their transmissions are occurring in a simultaneous manner. And there are multiple different schemes that allow this simultaneous transmissions to a particular access point, either a base station or a satellite or this sensor hub, etc. And how to do this simultaneous connections to a central entity is the topic of design of what are known as multiple access techniques. I believe that in your wireless communication course that you took last semester, you should have studied these multiple access techniques. One of them is time division multiple access. The other is called frequency division multiple access. And the third technique, which is popular, is called code division multiple access. And so it is this third technique, code division multiple access, is what we are going to look at. Now, I want to bring in one point at this juncture, which is this multiple access techniques can either be orthogonal or they may be non-orthogonal. When we consider time division multiple access or FDMA, frequency division access, typically the assumption is that different users' transmissions are orthogonal to each other. And that assumption more or less holds. When one user is transmitting on one particular time window and the other user is transmitting on a separate time window, and these two time windows are not overlapping, which is the case for TDMA, then these transmissions are not in any way going to interfere with each other. You receive first user in the first time window. That time the second user is not transmitting, so obviously that user cannot interfere. Then you go to the second user. That time the first user has been asked to not transmit. So again, you are receiving the second user kind of independently and on its own. And so TDMA is an example of what is known as orthogonal multiple access. Similarly, FDMA In FDMA, different users take different frequency bands. And it can be shown that the signals that are occupying two non-overlapping portions of frequency axis, they are again orthogonal to each other. In vectorial sense, you can picture them as forming 90-degree angles. So FDMA and TDMA are examples of orthogonal multiple access. There is an extension of OFDM, which is known as OFDMA, orthogonal frequency division multiple access, where also, as the name implies, the multiple access is happening in a completely orthogonal manner, meaning that different users are intentionally kept orthogonal to each other. And the reason for this orthogonal multiple access schemes is very clear. When one user is transmitting, you do not want the rest of the users to come and sit on top of this particular user. You don't want this user's transmission to be getting corrupted or getting interfered by the other transmitters. So the need for orthogonality in this multiple access schemes is very evident. And that is why actually this OFDMA is gained a lot of attention in context of 3G and in context of 4G systems. Now, recently, over the last maybe 5 to 7 years, the researchers have realized that the need for maintaining strict orthogonality may be somewhat self-defeating. It makes a lot of sense. Even intuitively, it makes a lot of sense. Suppose in one room, there is one central, let's say, speaker, and there are maybe 100 listeners. And the speaker then says, okay, I'm leaving the floor open for you to question me. And so that in that question answer session, what is typically done is this time division multiple access. One of the attendees wants to question the speaker, so he is given a time slot. And during that time slot, only that particular attendee is asking the question. Then in another time slot, some other person can ask a question. If suppose out of these 100 users, some 20 people have questions, and if all 20 of them simultaneously start asking questions, then obviously it's going to be a mess. You can't get the communication link, you can't get it to work in any meaningful manner. So maintaining orthogonality makes a lot of intuitive sense. But in this new technique, which is considered as the futuristic 5G technique, the idea is to do non-orthogonal multiple access. We intentionally allow some interference among different simultaneous transmitters. And unlike maybe what our human brain can deal with, the idea is that we would employ some very sophisticated algorithms at the base station to remove the interference from these simultaneous transmitters. And that allows us an improvement in the network level spectral efficiency. We can actually support more number of users, effectively higher overall aggregate system level data rate over the same bandwidth. So this model is pertinent over there. The CDMA is a very natural way to implement non-orthogonal multiple access. So let us look at the model of the signal at a receiver of such CDMA system. And we can write it like this. So there are a total of capital K simultaneous users. It's exactly the same way that we had denoted K in context of beamforming. And now we are kind of detailing out individual terms of these signals coming from different users. And so there is this term A of K, B of K, and S of K, T. And then there is this noise term. So let us look at these individual terms in isolation. This B of k is our symbol that we have studied in CT516. It can be a QAM symbol or it can be PSK symbol. So it is a particular information bearing symbol coming from the kth transmitter. This is a model where we are assuming synchronicity between the different transmitters. It's a simplifying assumption, but it will allow us to kind of get a full handle on the problem itself. And so in the case of synchronous receptions, we can consider only one period of symbol at a time. And so this here, the time variable t is confined to only one symbol duration. And over this symbol duration, different users' transmissions are synchronized. That is what is shown by the first term of this equation. We are bringing in a new notation and a new concept here, which is called the signature sequence. So this is some signature sequence of kth user. What is the signature sequence we'll be shortly looking at, but it is the signature sequence which allows us to do this code division multiple access. It is sometimes also known as the code of kth user. And we will assume that the signature sequence is normalized to have unit energy. Okay, so that is one assumption that we'll be making. And additionally, suppose if we assume that this B of k is also normalized to have a unit average symbol energy. I should have written it somewhere. So in that case, this Sk of t is having unit energy and this symbol also has unit energy on average. Then we can say that the kth user is transmitting an energy which is given by just the square of a of k. By the way, this a is a real number. It is real and positive number, or real and non-negative number. And so this, I don't have to do complex conjugation here. It's just the square of a real number which gives me the symbol energy. And this is possible because I've done this normalization. And then this n of t is a zero mean noise. We are not confining it to be just a real valued noise because this b can be complex valued symbols. And so in general, n will be a complex valued noise. And its variance is going to be, actually the variance of n of t is going to be unity. We are going to assume that n is normalized to have unit variance. And so therefore the variance of this entire term is going to be sigma squared. So I have a typing mistake here. But please keep in mind that it is not the variance of n which is sigma, it is sigma square, it is the variance of the entire noise term here which is sigma square. Okay, so let us look at what this different terms of this equation number 8, how they look like. And so here I am considering only one symbol, but for the sake of visualization, I'm going to now consider 3 symbols. Okay, just to make the visuals clearer. And in this very first drawing, I'm plotting this S of kt, and this is for some one user, maybe k equal to 1. Maybe this is for user 1. And these are the 3 symbol periods. So S of kt looks like this in this case. So it's just essentially a waveform with +1 and -1. In this case, it can be taking some other shape in some other examples, but this is probably the most typical example where S of k is taking values which are either 1 or -1. I have taken here that this S of kt keeps on changing this value every 32 units of time. So after 32 units, it became -1 to +1. And then it stayed +1 for the next 3 intervals, each of 32 units of time. And then after that, it again became -1. It stayed -1 for the next 32 unit of time. And then it again became +1. So that is Sk of t. And remember, Sk of t is not dependent on the symbol index. So the same Sk of t is going to get repeated at all the symbols. So you see the same pattern present in the different symbol intervals. Next, let us look at this B of k. And for B of k, I'm going to assume BPSK modulation. Remember, B of k were the modulated symbols. So let us consider the simplest case of BPSK. And in that case, B of k may look like this. Remember, this entire duration of 192 units of time is the symbol duration. And so the first symbol of BPSK is 1, then the second is -1, and the third is +1. Now I'm going to assume that A of k is 1. And so if I look at just the signal term of that equation 8, it is nothing but the multiplication of this symbol waveform with this signature sequence. And so what we end up getting is essentially a waveform which looks like this. What you will see is that in the first symbol, we are transmitting essentially Sk of t because Bk is 1. So when I multiply Sk with 1, it still remains Sk. In the second interval, I'm taking the Sk and just flipping the sign. It became the negative of the original Sk. And the third one is again back to the original Sk. So this is how the signal of the kth user that we are considering, how it will look like. Not the red lines, by the way. This red one is just the BPSK symbol. What is getting transmitted is this blue waveform, which is the multiplication of this red symbol waveform and the signature sequence, which is shown over here. And so this is how the transmitted signal of some one user looks like. But at the base station, we will be getting such transmissions from all capital K users. The only difference between the transmissions of different users is obviously, first of all, this B of K's will be different because different users are generating the symbols independently. The second difference is that as system designers, we would assign different signature sequence, different patterns of this Sk to different transmitters. Essentially, we will be separating these users by, or we will be trying to maintain sort of orthogonality. May not be a complete orthogonality, but something close to being orthogonal for different users by keeping these signature sequences to be carefully designed for this capital K users. Okay. Now, So this visualization was only for one user, and it was to kind of pictorially define the notations that were introduced in that equation 8. But there are several issues with these visualizations. So one issue is that the energy of these signature sequences is not normalized. In that visualization that we had, the energy over one symbol duration is not normalized. If I consider this time axis to have unit of seconds, who can tell me what will be the energy of sk of t shown on this shown in this diagram?
The same value as the time duration t.
Yes, Joel. So the energy of this sk of t is 192 in some unit of energy. Basically, the energy is calculated by taking the square of this waveform and integrating it over symbol duration, as we have done here. And the square of this waveform is obviously 1. And so now if I integrate 1 over 192 seconds, I get 192. So that is one limitation, that the energy is not normalized. But that limitation I can easily overcome by just multiplying this signature sequence by 1 over 192. So instead of 1 and minus 1, if I had 1 over 192 and minus 1 over 192, basically if I compressed y-axis, then that difficulty will go away. What do you think is another limitation? And that has to do with this diagram. So remember, we said that even our symbols are going to be assumed to be having unit energy. So I cannot really say that this first symbol is unit energy, because by the same logic, even this symbol has energy of 192. So this, what I'm showing is not really B of k, but instead of that, what should be the title of y-axis? Y-axis is not just B of k, because B of k has to have unit energy. But instead of that, it is A of k times B of k. Right? So that is one other clarification that I think you should keep in mind. Who can tell me what is A of k in this diagram?
One.
No, A of k is not 1. Remember, we said here, yes. So Anudeep is saying, I don't know if he's put it on the chat window that you can see, or okay. So remember, we said that B of k is unit energy. And so if I wanted to plot just B of k here, what will be the y-axis? In order to make this symbol to have unit energy, y-axis will have to be I just said it a moment ago.
1/192.
1 over 192, except, sorry, I think I made a mistake. It should be square root of 1 over 192. Because this is voltage, not power. So the y-axis will be square root of 1 over 192. If I plotted just the individual symbols, here I'm plotting value of 1. And so that is possible only if a of k is square root of 192. So that is something that you should keep in mind, that if we were plotting just b of k, then we needed to normalize that waveform. Alternatively, you can think that what we are plotting is a of k times b of k. In that case, we have to be mindful of what a of k is. Okay, the third limitation is that we have drawn, for the sake of ease in drawing such diagrams and also visualizing these diagrams, we show the pulses which were rectangular. In CT516, we have seen that almost no design which is practically viable uses rectangular pulses, at least for the wireless systems. Maybe for wireline, sometimes rectangular pulses are okay, but for wireless, we shouldn't be using rectangular pulses. So again, that was a simplification that we made. In practice, this chips of the signature sequence, and by chips, what I mean is these intervals of 32 units where sk of t can change polarity. These are known as chips, and they're different. Their name chip is to differentiate them from the bits, because otherwise they look like bits. They're ones and minus one, so they look like as if they are bits after going through BPSK modulation. But these are not bits. They don't carry any information. They are there just for allowing multiple access, and so this is known as the chips instead of bits. And so both the chips as well as the symbols typically have some raised cosine pulses instead of rectangular pulses. So these are the three main simplifications that we had made on this slide. One more thing that we have not included in the prior slide is that we just looked at the transmitted signal of this particular user in the time domain. If the user was transmitting without code division multiple access, then that user would be sending this red colored waveform, the BPSK waveform with rectangular pulse. But in code division multiple access, the user ends up sending this blue colored waveform. And that transmission we are illustrating as a function of time. What we haven't done in this diagram is how the red and the blue, how these two transmissions look like in the frequency domain. So that is not done. But remember, we have, in a way, at least for the discrete time case, we have seen the Fourier transformation of a rectangular pulse. Do you remember how we derived the Fourier transformation of a rectangular pulse? In what context did we do the Fourier transformation of a signal which is rectangular? Can anyone say that? Anudeep, we haven't talked about pulse shaping in this course. I'm saying in CT509. Inter-symbol interference. But again, Nidhi, I'm talking specifically about CT509. How did we, in CT509, where did we define effectively which was just the Fourier transformation of a rectangular pulse? W, capital W magnitude. Yes. Okay, yeah. Match filter. No, Nidhi. I think Anudeep and Arushi gave the right answer. So let us look at that very briefly. So in our earlier topic, if you recall, we derived the Fourier transformation effectively, which was a Fourier transformation. I didn't spell it out like that. This capital W term as this. And remember that we said that this is a very important derivation. But if you look at this derivation, you can see that this exp term is present in any Fourier transformations. And then typically in the Fourier transformation, there is an S of t term, basically the time domain signal whose Fourier transformation we are taking. But over here, that S of t is 1. So we can say that effectively what we are doing is a Fourier transformation. Transformation of a signal which is all ones. So that is what we did here. One difference is that in Fourier transformation, this exponent has negative sign in the bracket. That here is positive sign, but that is just an artifact of how we define this delta f naught. We defined it as f minus f naught. Instead of that, if we had defined it as f naught minus f, then it will be exactly the Fourier transformation. And we have seen the result of this derivation where we saw that it looks like a sink shape. And furthermore, the width of this sink pulse is inversely proportional to the width of this rectangular pulse. So when the rectangular pulse has a width of some 5 units, then you get a sink shape which is kind of broad and wide, the red colored one. But if we make the width of the rectangular pulse to be bigger, maybe almost twice as much, then the sink shape kind of shrinks by about the same factor. It becomes, it has a width which is roughly half of the red colored width. So this is what we had seen earlier. So in that context, now over here, what we can say is that compared to the spectrum of this original symbols, which will have a width which is roughly proportional to 1 over 192, meaning that it will be pretty, it will be occupying a very small frequency spectrum. Compared to that, this transmitted signal will have a width which is 1 over 32. because individual chips are now only 32 units in time. So obviously, because we are shrinking in time domain the width of these pulses, in the frequency domain, just like what we were looking at a moment ago, the spectrum is going to get spreaded out. In this case, it is going to get spreaded out exactly by what factor? What will be the factor by which the original spectrum of these symbols in the red will get spreaded, because we are multiplying it with this S of k. It will be essentially the ratio of 192 with 32. So that ratio should be 6. So basically, if I look at the spectrum without this code division multiple access, compared to that spectrum, the spectrum of this code multiplied symbols will be 6 times wider. And so that is why this scheme is sometimes also known as spread spectrum scheme. So that is something that you have to kind of consider, that by doing this code division multiple access, I'm spreading the spectrum. Whenever in time domain we start making changes faster, in the frequency domain, we get a spreading effect. In the time domain, our original symbols were changing only at the rate of 1 every 192 seconds. Instead of that, because of the presence of this signature sequence, we are now making changes on a much faster, at a much faster rate, every 32 seconds. And so therefore, the signal gets spread out in frequency by a factor of 6. Okay, so those are some of the things that we need to be aware of. But otherwise, I think the concept behind that equation 8 should be pretty clear to you now. Now I'm going to move forward, and I'm going to define that same equation 8 in the linear algebraic term. So I'm writing the exact same equation, summation over k of ak, bk, sk of t, in a manner which should remind you of what we have done for CT516. I stacked all of this S1, S2 up to S of k, the signature sequences, as columns of a matrix that I'm calling S of t. The amplitude of different users, I'm making them to be a diagonal matrix called A. And the symbols that are transmitted synchronously by K users, I am collecting them into this vector B. And so YT became S of t times A times B plus the noise. Now, although this equation may look to you different from the earlier equations that we have seen in the context of beamforming, it is in fact not that different. How can you draw an analogy between this equation and the equation for beamforming that we have seen earlier? Okay, who has not spoken yet? Komal?
Yes, sir. Hello.
Yeah.
Sir, if S of t into A will be equated as W Hermitian. Then Y of
Um,
T will be. Hello.
T times A is W Hermitian. Why W Hermitian? I'm asking you to compare this equation with equation 2 on the very first slide.
Okay, sir.
2, we didn't have W Hermitian, we just had W. So, but yeah, okay, fine. So S of T, we can kind of consider it as that matrix W. Okay, Nidhi, what about the other analogy? Can you draw some other analogy? What is this vector B? How was it denoted earlier?
It is a symbol vector.
Yeah, so it was symbol vector S. And now this diagonal matrix A is something new. I would say that this diagonal matrix A was kind of absorbed in our earlier symbol vector. What we were looking at in that equation 2 was a symbol vector which was A times B. Here we have separated it out. And the reason is because we are assuming this B1, B2, all of the B symbols to have unit energy. That is just for notational sake. Obviously, the received signal will not have all the symbols at the same unit energy. And so what is the energy of each of these K users is captured by this A1, A2, A of K. Because these B's are assumed to have unit energy, the S's are assumed to have unit energy, the symbol energy is just proportional to A squared. So you could also think of this diagonal matrix as defining the square root of symbol energy, square root of ES1, square root of ES2, and so on. And in our earlier formulations, this symbol energy was kind of absorbed in the symbol vector. So that is one slight difference that we are making. But other than that, we can actually proceed in the same manner as what we have done earlier. And we can, okay, so before doing that, remember we had defined this correlation matrix, R. So we will define a correlation matrix in case of CDMA also, whose individual elements are the correlation between ith and the jth signature sequence. And because the signature sequences are considered to be continuous time, we will have to do this integration. When you implement this CDMA technique in MATLAB, typically what we do is we sample this signature sequence only one time per chip. In simplified simulations, we would sample the signature sequence only one time per chip. That will mean that each symbol we are sampling 6 times. But the signature sequence will be then just a vector of 6 cross 1. And that vector will be -1, 1, 1, 1, -1, and 1. Right? So in our simulations, we will be actually having this S1 as a vector of 6 cross 1. It will be some random pattern of 1s and -1. Then S2 also will be some other random pattern of 1s and -1 for the second user, and so on. And so now this S of T will actually be just a matrix which is filled up with random 1s and -1s. And then this correlation will not require this integration. It will be just summation of those 1s and -1 for two different users. Now we can show that this correlation coefficient is guaranteed to be taking a value between -1 to 1. So why is that? Can anybody tell me? Kishan? Yeah, go ahead. So Anudeep made a good point. We are considering normalized signature sequences. So the elements of that vector or matrix that I was saying will not be 1s and -1. There will be appropriately normalized values, but the polarities will be either positive or negative. So Kishan, can you tell me why this is the case? Why this correlation coefficient is guaranteed to be less than 1 and greater than -1? Kishan, are you there?
I'm just thinking.
Okay, fine. So Kishan is thinking. So let us go to who is next. Priyanjali, are you there? Priyanjali? Divya, yes. S of t is a random sequence of 1s and -1s, except it is not exactly 1s and -1 because, as Anudeep pointed out, we are normalizing the energy so that the polarity is positive or negative. Okay, Priyanjali, if you are there, then please or let me unmute you. Actually, Priyanjali is not even connected on audio. Priyanjali, if you are there, you can put your answer on the chat window. If I don't see answer from you, it means that you just logged in, but you are not at your desk. So Priyanjali actually just logs in and then she goes away, it looks like, which is unfortunate. Okay, who is next? Divya, what do you think? Let me put it this way. When we said that this energies of the signature sequences are normalized, what does it mean in context of this rho ij? Look at this equation here and compare it with the equation written over here.
So can I try?
Divya, you have anything
Yes,
to say?
sir.
Yeah.
So whenever we are finding out energy, we are finding out the autocorrelation. So that is one. That is the energy of the signal.
Yes, signature sequence, yes.
Yes. So when we are finding out the cross correlation between different users, like they are either like not related to each other or they are related to each other. So always there will be a sign difference if they are not related. And if it is
Yes.
normalized, it will be -1. And if they are same, I and J are same, then it is +1. So it will always be between -1 and +1.
Okay. So that is fine. Can you put that in little more mathematical way? Yeah. So Anudeep had the right answer, but what would be a way to think of this equation over here?
So when we put I equal to J, basically we are calculating the energy. So when I equal to J, sir, when there is maximum correlation, that is when I is equal to J. Like we are having the same term. So correlation between I and J, when I and J are different, will always be less than when I is equal to J.
Yeah.
So if I equal to J itself is normalized, then I is not equal to J will always be less than that. So it will like obviously be.
Okay. I want even more crisp answer. Yeah, exactly. So Bibin mentioned the answer. Remember, we want to think of this Si and Sj to be vectors. A lot of the times, vectorial viewpoint helps. When we say that these individual signature sequences are having normalized energy, what will be the length of the vector? In terms of vectorial viewpoint, their lengths will be 1. And this integration in terms of vector will be just a dot product. Now you know that if I have some two vectors, let's say A and B, and I'm taking dot product of the two vectors, the result can be written as the length of A times length of B times cosine of the angle between the two vectors. But the individual lengths, we have already said they are 1. So effectively, what this correlation coefficient is measuring is the cosine of the angle between these two vectors. Obviously, that angle will be 0 when we are considering the same vector, and that is when we will get 1. And for all other vectors, the value has to be between -1 and 1 because cosine is always confined to this value. Okay, so that is how we will formulate the correlation matrix R. So this R is kind of slightly different from R that we have seen earlier. There the correlation elements would not be normalized because we didn't pull out the symbol energies as a separate diagonal matrix. And therefore this elements of columns of this matrix were not having unit energy. So this R is that way slightly different from capital R matrix that we had considered earlier. And the only difference is that in that earlier formulation of R, there will be the same term rho ij, but that rho ij will be additionally getting multiplied by the square root of symbol energies of ith and jth transmitter. Basically square root of ai times square root of aj. So that is one difference that we are making. It is kind of not a fundamental difference. It is just a way of writing the original formulation in a manner which makes it little more mathematically easier to handle. But otherwise, we can just proceed in the same manner that we have done earlier for the two cases of beamforming. We define this correlation matrix. We take the received signal y of t. Remember, y of t was defined here. This is our y of t. So we take that y of t, which is also defined here, and we correlate it with this matrix S. And when we do that, we get an expression which looks a lot like that beamforming equation, except the symbol energy matrix, the diagonal matrix A is present because this R is now normalized. But eventually, we get a vector here. This Z is not a function of time anymore. It is a vector. And so this is now very much analogous to what we saw in the context of beamforming equations. And so we can do the same decorrelation step or MMSE step. Okay, so this is a way to kind of think of CDMA as fundamentally being quite equivalent to the other operation of beamforming that we had looked at. The benefit of this view is that now, suppose if we come across, or if somebody throws to us some fancy names like Wiener algorithm or MVDR algorithm, that we would be looking in the context of beamforming, we would say that, okay, those algorithms are applicable for CDMA also. Okay, so that is the main thing that I wanted to look at. This actually completes our design formulation. What the CDMA receiver will look like is completely captured here. Now let us do some performance analysis. Let us try to study this CDMA reception in a little more granular manner. Maybe go down to the little nitty-gritty details of what this receiver will look like. And we will be doing this study in the context of the single user mesh filter. Do you remember this term that we had introduced earlier? So who has not spoken yet? Soumya is not here. So I'll go back to Arushi. Arushi, do you know what single user mesh filter is? And where did we bring it in? Arushi?
Yes. Hello, sir. Am I audible?
Yeah. Go ahead.
Sir,
Do you remember in what context did we bring in this single user filter? Single user receiver?
sir, when we were doing beamforming at that time only.
Yes. So it is mentioned on this slide number 7, where we said that a single user beamformer, what will it look like? And what would be the formulation of this receiver? So we had seen it in that context. So now, I mean, if you, oh, by the way, did I put these slides on Google Classroom? I don't remember. If I did not, then I will post these slides over there today. But so that is essentially what we are now going to look at in the context of CDMA scheme. And the benefit is that once we have kind of connected the CDMA with the beamforming. What we are going to discuss now, although it is in the context of CDMA, it actually carries the concept applies also to the beamforming problem as well. So this is what we'll be doing over next some 10 minutes or so. I'll be taking a quick break. I'll be back in some few minutes. Okay, I'm back. It's about 1 hour and 15 minutes into the lecture. So maybe let us just spend about 5 minutes on this. I don't think we'll be able to wrap it up today. Because I also want to show you some few papers in connection to the lab that you are doing. And so, okay. So we'll look at the single user mesh filter. And in that context, suppose if I perform just the single user mesh filtering on this y of t, so instead of doing all of this, so instead of doing this stepwise processing, suppose if I perform single user mesh filter on y of t on the received signal, and I collect all the outputs of all of those single user mesh filters, then what will be the form of that single user mesh filter outputs? That is my question to you. Each user is doing its own single user mesh filtering. Each user thinks that that user is the only active user present. The remaining k-1 users are completely getting ignored. Okay, Arushi just spoke. So Anudeep, you have any idea? Okay, who is next? Joel, what do you think?
Sir, I think each user will get its what signature, and the output will be composed of those signatures.
Yeah, I'm asking, what is the mathematical formulation? Komal?
So
What
that R will be W. I mean W Hermitian. Like y is equal to some if y is equal to RW, then R is our W Hermitian.
Yeah, okay.
So is k is 1, that each user is thinking that k is 1. The r will be a scalar, so it's just division of that. The received signal divided by r will give you the estimate.
Yes, but what is R now? We already went
Yes.
in our CDMA context. R will be for each user. If each user thinks that that user is the only user present, for that user,
Solution is.
Yeah, what is that?
Correlation coefficient and
Coordinator.
For the same user, S Hermitian S gives us what? We just went over.
The energy of the signal.
And what is that?
AK square.
No.
Unity.
Cos theta util SI of t into SJ of t. That will be cos theta, that angle between them.
Yeah, but theta is now 0, remember? Because each user is doing this correlation with its own signature sequence. So that R will be just 1.
1, yes.
So the division that Divya was talking about is not needed.
No, yes.
So what do we get? Essentially,
Yes, that.
when each user is doing just the single user mesh filtering, what we get is this vector Z. Does it make sense?
Yes.
Why does it make sense?
Um, value of R will be 1 for this case.
Well,
And
yeah, I mean, that is what Divya was saying, that this R inverse, I don't need to do because R is just 1. And so
B hat will be Z.
B hat will be same as Z. I mean, if I'm doing decorrelation, then for the single user mesh filter case, the decorrelation will be a degenerate form in which I'll get B hat, which is same as Z, because this R inverse is going to be an identity matrix. All its diagonal values will be 1. But what I'm asking is why this Z is the output of mesh filter. You see where my cursor is?
Yes.
This Z that I'm forming like this, I am claiming that this particular mathematical operation I'm doing actually gives me the output of the mesh filters, the single user mesh filters at all of these K users. And my question is, why is that the case?
Sir, in that Z equation, if we substitute B equal to B hat, we'll get that.
V equal to V hat, what is V?
RA plus sigma, in that, if, instead of B, we replace our decorrelated term, our estimate, R inverse Z, then, sir, we'll get back our.
No, my question is, by doing this operation as Hermitian Y, why do I get the output which I can call single user mesh filter? Maybe let me go back. Even in this notation, what I'm saying is this vector Y, I can say that this vector Y is the single user mesh filter output. Why can I say that? What is the definition of mesh filter?
There will be only one W that will be giving the maximum peak of the sync function.
Yeah, mesh filter assumes that only one user is present. And so let's look at the first element of Y. I am claiming that that first element of Y will be the output of single user mesh filter used by first user. If the first user thinks that I am the only transmitter present, then the best thing I can do is single user mesh filtering. And so that is what the first element of Y will be like. What will be the first element of Y? Who can tell me? The first element of Y will be the dot product between the first column of W with X. Right? That will be the first element of this vector Y. The dot product of first column of W with X. But the dot product of the first column of X is this vector. And this is the vector that we have called the match filter for the first user. Remember when we talked about the discrete Fourier transform based power spectral density estimation for solving FOA problem? That in that context, we had brought up this match filtering. And we were saying that time that if I take the filter coefficients to be the same as the column vector of W, then my filter is matched to the transmission vector or the array vector in case of antenna systems. And that is why when the filter coefficients are matched to the array vector, we get match filter. And so over here, if I think of this vector Y as coming out of total of capital K different filters, then all of those K filters are actually matched to the individual array vectors. The first filter is nothing but the first column of W, second filter is nothing but the second column of W, and so on. And these columns are matched to the array vectors. In case of CDMA, those filters are matched to the signature sequences of different users. This S of T, remember, is the signature sequence. So when I do S Hermitian T times Y, for the first user, I am matching the filter to be same as S1 of T. The second user's filter is matched to S2 of T, and so on. And so the output of single user match filter is nothing but the Z. If you close your eyes and say that, no, I am the only user present, even if there are 99 other users actually present other than that particular user, if you bury your head in the sand and say that, no, I don't want to deal with all that interference, then this is actually the optimal strategy, the match filtering. That is what we did even in CT516. There it was actually optimal because these individual columns of this S matrix were all orthogonal. Remember, these are now the basis functions. And in CT516, this basis was orthonormal. When this basis is orthonormal, then the match filter is the best operation. And therefore, in CT516, all that we did was just match filtering. All that we did in CT516 was this first step. And that step was sufficient because when the basis vectors are orthonormal, this R becomes identity matrix. And I get the signal back without any corruption from the other interferers. But in our case, this orthogonality is not present. These rho values may be non-zero. And so now we have to deal with matrix R, which is present there. The presence of matrix R says that this vector Z, which is the single user match filter output, will have contribution not only from the user of interest, but this R is going to cross couple the symbols of the other users also in an element of vector Z. So the answer to this question is that the single user match filter output is nothing but this vector Z. Okay, so we will stop here and then we will continue this discussion next time. I would like you to pay close attention to this next discussion that we'll be doing, because only when we start looking at these equations in this type of low-level detail is when we start appreciating the concept in a much greater depth, with a much greater depth. So hopefully, when we meet next time and go over a particular topic of performance analysis, we will be considering a very simplified case of performance analysis, because otherwise the equations become kind of complicated to fully understand. But hopefully it will give us a good conceptual insight, not only into the performance of the single user match filter, but also with that we'll be able to understand what this decorrelator is doing for us. Okay, so that is what we will do next time. And now let us see. We have maybe, I'll take maybe 10 more minutes, and I want to bring to your attention some two different papers that are actually quite relevant to what you are doing. Okay, so this is one paper. It appeared in IEEE Transactions on Communications about 2 years back. So this is about a 5G technique called massive MIMO. And there's one one additional aspect that we haven't talked about too much. It is actually entirely a practical aspect, which is called hybrid beamforming. This hybrid requirement comes because when the MIMO has massive number of antenna elements, they're talking about maybe not only some in multiples of tens, but rather in multiples of hundreds. The problem comes because there'll be a significantly high RF cost. If you have 1,000 antennas and if you have to put RF circuit behind each of that antenna, then the requirement becomes too much. And so that is where the concept of this hybrid processing comes. And this is this has become a very prominent topic in communication literature. Massive MIMO with hybrid approach. What they have done is essentially your CT509 lab number 3 that you are doing, where their goal is to estimate the direction of arrival. You are able to see this, right, by the way?
Yes, sir.
They're trying to estimate the direction of arrival using a massive number of antennas. But they are doing that in this hybrid manner. And so what is meant by hybrid? What they do is they have large number of antennas that they're calling some n times m or something. Let me see where they're saying that. Sorry, m times k. The total number of elements they have is capital N. And this N can be very large. So what they do is they divide this large array into such sets. Each set has m elements. And there are total of k such sets, capital K. So this y1 to yk. Now, to reduce the RF cost, they put the RF circuit, the A to D converter, and even all this digital processing that is needed. They put only one such hardware for the entire subset of M elements. One freedom that they have is they can combine the antenna output of each of this, what they call sub-array. So this sub-array has M elements. I mean, let us take an example. Suppose they have a total of 100 elements. Capital N is 100. 100 is too many RF circuit to put. It will be too expensive. So I'm going to divide it up into 10 sets, or let us say not even 10, 5 sets of 20 subarrays. This M is 20, and there will be 5 such sets of those subarrays. One thing that they are allowed to do is they can put some analog phase shifter, which they are showing by this symbol, on each of these 100 antenna elements. But then they have to combine the output, possibly after phase shifting. Phase shifting is optional. If they want to do it, they can do it. Otherwise, the output will be just getting combined. In this case, now they will get only 5 outputs. And each of those 5 will be phase shifted summation of 20 different antenna outputs. Does this make sense? This is the key figure of hybrid beamforming or hybrid DOI estimation. What do you think? Makes sense? What they're doing? Do you understand? What they're doing and why they are doing it? Who can say this? Nidhi? Nidhi, are you there?
Yes, sir. I'm thinking.
Okay, you are thinking. So who is next? Divya?
Yes. They are basically combining, so instead of using capital N such RF hardwares, they are combining into M sets, sorry,
Yeah.
K sets of M elements each, and then they are using the K such hardware.
Correct. Correct. Yeah. So this is entirely kind of, this is not coming from some high level, fundamental, some really nice, elegant, mathematical requirement or reason. This is actually coming from the entirely the opposite side. This is coming from the rock bottom economical aspect. This entire diagram, the motivation for this diagram is completely economic based. If you're putting such antennas on the top of a tower, the tower will become very expensive if you have to put 100 RF hardware. Instead of that, if you can just do with 5 hardware, then it becomes economically feasible. And so the entire research activity that is going on in hybrid beamforming is getting motivated purely from the economic terms. The reason why it is called hybrid beamforming is because this part can be also thought of as beamformer because they have these phase shifters. And remember, the single user mesh filter is nothing but a phase shifter in the context of beamforming. And that can be done entirely in the analog domain. So this is the analog domain beamforming. They have an option to do maybe decorrelator. For that, they need to do matrix inverse and a whole lot of other things, possibly. Any fancy algorithm they want to implement, they can do it here. That they have freedom to do. So that is why it's hybrid of analog and digital. The reason I want to bring this to attention is that what you are doing in CT509 is essentially the objective of this paper. They want to do DOA estimation not when all of these 100 elements have corresponding RF circuit. They want to be able to do it when their hands are tied and their design is constrained by this diagram. Then how will they be able to do DOA estimation is the topic of this paper, written 2 years back. So they have defined this array vector very much like the way we have defined it. By the way, they are considering only one source. They are not even considering this multiple source models that we are now looking at. So it's a very simple problem. This is just a single source problem. All that they want to do is to be able to figure out this theta naught. They're calling this phase alignment DOA estimation, which we have called the match filtering algorithm or the discrete Fourier transform based power spectral density algorithm. Over there, remember we did Y Hermitian and we took an average of that, and that we called as the estimate of power spectral density. That they are calling to be RB Hermitian. So this is very much similar to what we had looked at. For the conventional analog phase alignment, where all of this is just completely done in analog, they have said what will be the output of this type of mesh filtering. And it turns out to be very much similar to what we had done. Somewhere I will show you that formulation. Yeah, right here. Remember this series that we had seen? that capital W series, what we call the most important series of signal processing. That is their equation 28. And this is nothing but the sinc function that we have seen. Their only novelty, at least in terms of this power spectral density based estimation, is that compared to what you are doing, if suppose you were constrained to do this, then what would be the mathematics? So that is what they're calling hybrid analog and digital phase alignment based DOA estimator. And that is what they have analyzed here. What type of phase shift they would want to put on this analog part, what type of phase shift they want to put on the digital part, so that they get the angular spectrum, whose peak will tell them the value of theta naught. That is all. Exact same mathematics and simulation that you are doing. The only minor, I would say minor, but that is the content of this paper, is they are breaking down the phase shifting before doing this power spectral density calculation. They are bringing it down, breaking it down in these two phases, analog and digital. That is the entire content of section 3. What they call this phase alignment based DOA algorithm is nothing but our power spectral density based evaluations. Okay, so that is the first part. In the second part, they took the music algorithm and they modified the music algorithm so that it can work with this hybrid arrangement. So that is shown over here. Remember this equation that we have seen for the correlation matrix. Then this is where they're doing the singular value decomposition. Because they have only one source, in the singular value decomposition, there will be total of, all the eigenvalues will be equal to the variance of the noise. There will be only one eigenvalue which will be stronger, which is shown by this matrix. And this is the music spectrum, pseudo spectrum that we have seen. So in fact, they are saying that they modified the music algorithm, low complexity hybrid music algorithm, but the concept are heavily reused. This equation 42, 43, all of this you could have written it yourself based on what you know. So the entire paper is, the concept wise, it is not difficult at all. It's a very simple extension of your lab 3 of CT509. One other thing that they have done, which is pretty good actually, which is the Kramer-Rao estimate, Kramer-Rao lower bound on the DOA estimation. This we haven't done in our class, but they have derived the CRLB for the DOA estimation, and that is what they are showing here. The dotted line is the Kramer-Rao bound, and the solid lines are their simulation performance, and they are showing that their simulation output is matching in terms of the theoretical Kramer-Rao analysis. And they are showing that if suppose they have total of 32 elements and they create subarrays of size 1, 2, 4, and 8, what will be the performance? Obviously, when the subarray size becomes more, the performance deteriorates. But still at 10 dB, they get a pretty good angular estimation. It's less than, I would say maybe 0.2 or 0.3 degrees only. If you can estimate the direction of arrival to the accuracy of only 0.3 degree in the standard deviation, that is pretty good. So that is what their entire paper is about. And they have applied it to something which is very much 5G. They have applied it to massive MIMO, and they have implemented the hybrid implementation. Whenever you put the word massive MIMO and hybrid together in the title of a paper, that paper gets a very high interest these days. Okay? So that is one paper that I wanted you to bring to your attention. I think we are already hitting noon. It's 12 o'clock. So the other paper, maybe I will not show to you right now. I will conclude today's lecture here. Maybe some of you may have other commitments.